Hi everybody. We have here example for series resonance. So let's go ahead and start solving the problem. The first question is, what is the value of L, the inductance of the inductor, in millihenry? All right. If the resonance frequency is 1800 hertz, so the frequency of the resonance is equal to 1800 hertz. So let's first define what is the resonant frequency. What happened at resonant frequency? What happened at resonant frequency that the impedance of the inductor is equal to the impedance of the capacitor, and they will cancel each other, and in the end you will have resistive circuit. What does it mean by that? Well, if you want to calculate the total impedance on the circuit, you will say R plus JXL, the inductance of the inductor, minus JXC. That's the total impedance of the circuit connected in series. So you can write it like R plus J, and you have XL minus XC. So what happens if XL is equal XC? If XL is equal XZ, so they will cancel each other. It means XL equal C, so the total will be equal 0 in this case. So accordingly, the total impedance at resonance will be equal to R. All right, that's at the resonance frequency 800 hertz. So, okay, so that's the condition that XL is equal XC. That's the key. Well, let's figure out how to find the relationship. XL is equal XC. What is XL? Is equal omega L. What's XC? It's equal 1 over omega C. So if you multiply like that, that's omega L over 1. So 1 over 1 is equal 1. Omega L times omega C. So the answer will be omega square LC is equal 1. So in this condition, it will shows the relationship between the frequency at resonance, LC. In this problem, it's required to find the value for L that it will cause or will make the circuit work at resonance. So what is the value of L? From this equation, you can say L will be equal 1 over omega square C. That's the value of L that will make the circuit operating at the resonance. So L is equal 1 over omega. Oh, first, what's the value of omega at resonance? It's giving that the frequency at resonance is equal 1800 hertz. So you convert this to angular frequency. So let's just write the resonant frequency is equal 1800 hertz. So the resonant frequency radian per second will be equal to YF, will be equal to pi times 1800. That will give 3600 pi radian per second. All right. So if you like to evaluate the value, you can do it, but we'll leave it like that. Well, now I'm going to substitute by omega R in the equation here to find L. So L is equal 1 over omega R now is equal 3600 pi, make it square, times the value of C. What is the value of C in this example? 2 microfarad. How you write 2 microfarad? 2 times 10 negative 6. That will give it in Henry. If you want to convert this to millihenry, multiply it by 1000. It will give the value for the inductance. Do that in the calculator. You'll find that's equal to 3.9 millihenry. So the value of the inductance that it will make the circuit operate at the resonant frequency 1800 hertz is equal 3.9 millihenry. So we answered the first question. All right. Let's go now for the second question. Second question, this problem is, let's calculate XL and XC. What is the value of XL? What is the value of XC? And how you compare them. All right, so to do that, it's easy. How you find the value of XL? We know that the equation of XL is equal to omega L. and you are calculating this at the resonant frequency, which is equal omega r. Let's go ahead and calculate it. Omega r is equal 3600 pi, and L we already found equal 3.9 millihenry, so multiply it by 10 power negative 3, and round the number, we'll find that's almost equal to 44 ohm. What about the value of XC at the resonant frequency? It's 1 over omega C, omega R. So 1 over 3600 pi, and the value of the capacitor 2 times 10 negative 6. You found is equal 44 ohm. So what is the relation between XL and XC at resonance? We found that XL, XC, and we expected that at resonance because they will cancel each other. Now let's go for another question. C. What about to calculate the magnitude of the current at resonance? So if you want to calculate the current, and let's talk about the root mean square value of the current at resonance. How to calculate that? Well, we agree that at resonance, L and C, the impedance of the inductor and the impedance of the capacitor cancel each other. So what's left? Only the resistance, 4.7 ohm. So the equivalent circuit in this case, you can do it like a resistance equal to 4.7 ohm. L and C will cancel at resonance. So you can just have the circuit with the only resistance. And you need the root mean square. We know that the value of E is equal to, I think 20 millivoltage, 20, yes. E is equal to 20 sine omega t and given in millivolt. So that will be the maximum value, will be equal to 20 millivolt. To calculate the current and root mean square, you got to express using the root mean square. So what is the root mean square value? That will be equal to 20 divided by root 2 millivolt. And if you wish to express as a phasor, it's an angle 0. So you say 20 over root 2 an angle 0. Just, you can assume it in an angle 0. In any way, that's the root mean square of the voltage in the circuit. And since you have only resistance here, as you see, at resonance, so to find the current, yes, just use Ohm's law. It will be equal the voltage divided by the resistance. In this case, you will have 20 divided by 2 and divided by the resistance, which equal 4.7. Remember that it was in millivolt. So when you we're getting in milliamp, right? Doing that, then you will get 3 milliamp. So that's the current, the root mean square value at the resonance. Great. So that was simple. Let's go to part D in the same problem. Let's try to find the power dissipated by the circuit at resonance. So what is the power dissipated in the circuit at resonance? Well, since at resonance you have only resistance, so it will be dissipated by the resistance. And we know that the power in this case at resonance is equal I root mean square at the magnitude only and multiplied by the resistance. The current is equal to 3 milliamp, so it will be 3 over 1,000 square times 4.7. Okay, so when you do that, you will find that's equal to 42.3 times, because we have this like 10 power 6 watt. Let me just clear. (42.3) times 10 minus 6 watt. That would be the power dissipated in this circuit. Okay, great. So of course you can convert it to milliwatt, whatever you wanna calculate, but this is in watt. Okay, let's now find part E. In E, it's required to find the apparent power delivered to the system at resonance, apparent power. Delivered to the system at resonance. We know that apparent power, if you remember the triangle, for power triangle, you have here the power, reactive power, S. So the one S. But at resonance, XL and XC, they are cancel each other, and the circuit is resistive only. What does it mean? It means in this case Q is equal 0. So at resonance, you can say that S is equal to the power because Q is equal 0. The reactance of the impedance of the inductor and the capacitor cancel each other, be 0. So no reactive power is consumed. So in this case, you can just write S at resonance is equal the power at resonance, which is equal 42.310 negative 6 watt. That is easy. You see, once you understand the concept, it's just you can get the answer in few seconds. Let's get part B. We calculate the power. Let's say that we need to calculate the power factor at resonance. Well, since the circuit is resistive and no reactive power, all power, so you have P equal S, so the power factor would be equal 1. So it's equal unity power factor. We know that for resistive circuit. Excellent. So at resonance, the circuit has unity power factor. All right. Let's find part G. Let's calculate the quality factor Q. Calculate the power quality Q. Q, by the way, is not the reactive power here. Q is a different thing. That's why I write power quality, not the reactive power. The definition of power quality Q, it's defined by many equations as explained in previous lecture, but let's just use the basic one, XL over R. So XL is the reactance of the inductor by itself, with which we found that equal to 44. Let's just check XL, we found it. Yeah, 44 ohm. All right. And the resistance is equal 4.7 ohm. So that's why unitless. When we divide that, we'll find this equal to 9.36. That's the quality factor of the circuit that we have it right here. Well, so that's the quality factor. To distinguish between the reactive power and quality factor, let's call it QR, quality factor QR, right? Well, let's say that we want to find the bandwidth also. How you find the bandwidth? First, what's the bandwidth? Well, if you have the current curve or power curve, whatever, against frequency, that's the frequency. This is the current or power. You can have the y-axis current or power in the circuit. Both they have the same shape but just different value. We know that the top or the peak value of current or power that happen at the resonant frequency, and then the cutoff frequency, which is equal F1 and equal F2. At the cutoff frequency, we know that the power will be equal half the maximum power, so it will be equal B max divided by 2, and the top part here, it happened D max that we calculated you the maximum power at the resonant, just to remind you, is 42.3 times 10 negative 6, or 42.3 microwatt. So at the cutoff frequency, it's equal half, and the bandwidth will be the difference between F1 and F2. That's we call it the bandwidth, what is BW. So how we calculate the bandwidth? If you know the quality factor Q, there is a simple equation we can use. Say that the bandwidth is equal to the resonant frequency divided by the quality factor. And the resonant frequency, if you use it hertz or radian per second, both are okay. So the unit of the bandwidth depend on the units of the resonant frequency. The resonant frequency we have in this problem is 1800 hertz divided by the quality factor, which is equal 9.36. So when you divide that, you get 192.3 hertz. So you know this bandwidth from F1 to F2. If you can write, you can say it's F2 minus F1 should be equal to 192.3 hertz. That's the bandwidth. Easy. Let's go to the next one. Let's say that we want to find the cutoff frequencies, all right, and the power distributed at it. The cutoff frequency, how you find F1 and how you find F2. I gave in the last lecture a simple equation for that, used with Q, or if the quality factor less than 10, we're going to use the following. We say that omega 1 is equal minus A plus B, and omega 2 is equal A plus B. So what is A? A was defined as, I'm just reminding you about the formula, is equal R over 2L. So in this case, A equal R over 2L. Let me just do it in the calculator. It will be 4.7 ohm divided by 2L, and L is equal to 3.9 millihenry, so 10 negative 3. So you get 602.6. That's A. Let's find B. What's B? B is defined as, let me just first find B square. It's easy to remember B square. B square is equal A square plus 1 over LC. So A square, you got A, 602.6 square plus 1 over LC. L is equal 3.9 times 10 negative 3 because it's millihenry. And C is equal to 2 microfarad, 2 times 10 negative 6. And you calculate B square, and then you find the square root of B squared. That will be equal to B. You do that, you get 11,339. So that's the value for B. So you got B, and you got A. That's A. So now we can find omega 1 and omega 2. So omega 1 will be equal negative A plus B. That's equal to 10736 radian per second. And omega 2 is equal A plus B. You add them, you get 11941 radian per second. So that will be so we found the cutoff frequencies, but in radian per second. Now you convert it to hertz. Very simple. You will say that the frequency F1, the first cutoff frequency, is equal omega 1 divided by 2 pi. So you have 10736 divided by 2 pi. You get 1708.7 hertz. Find the F2 using the same equation, omega 2 divided by 2 pi. Omega 2 is equal to 11941 radian per second divided by 2 pi. You get 1900.5 hertz. So that's F1 and F2. That's the cutoff frequency. And of course, if you're asked to find the power at cutoff frequency, you say the power at F1 is equal, the power at F2 is equal half the maximum power. At resonance, it means equal half. What is the value for the maximum power? We calculated 42.3. 42.3 times 10 negative 6. And you get, here you go, you get 4 by 2 is equal to 115 times 10 negative 6 watt. So that will be the power at the cutoff frequency. It was equal half the power. So that's how you solve the question related to series resonance. And you can check your value that you obtain for F1, F2, you subtract them. It should be very close to the bandwidth we just calculated in the other problem. That should be close to 192. Okay, that's all. All right, I hope that you enjoyed.